Alrighty, I guess I don't have to speak too loud today because I can hear myself. So that's great. Good morning, everyone. Okay, so we're gonna go into the last day of the course today. Well, we're gonna talk a little bit about stabilization. Soil stabilization has to deal with all these problematic soil that we saw with low volume roads and also to paved roads. And obviously, with the time we have today, only 2 hours, we're going to go into very general considerations of mechanical and chemical stabilization. So what you're going to be learning today is about, chemical and mechanical stabilization, and I'm going to round it up on the second hour into the use of geosynthetics in roadway systems. Okay, so why subgrade improvement? Well, it is I put in here extremely important if you want to ensure that it's going to be a long-lasting pavement structure without excessive maintenance and movement, right? Usually we avoid soils that are problematic. We just excavate, right? We just get rid of the soil as much as we can and as economically feasible as it is, right? As we can be. But when excavation is a problem, then the soil is not economically feasible to do that, and you need to stabilize that soil, right? So the objectives of stabilization can be probably summarized in few areas. One of the strength, the strengthening of the so everything has to do with the strength or not. Another one is the soil workability. Sometimes not even the stabilization has any value into the design of the road, but you need to do that in order to even start working on that, just to get the loaders and to get the equipment to start working on compacting the soils. Weather resistant work platform, and this one also goes into the workability at the beginning during the construction stage of your road. Swelling, now volume change, reduce swelling on expansive soils that you've seen the problem around, and mitigate also problems when we do have frost heave. The objectives, like I said, let's put them into stages in the construction. The first one will be the construction platform, right? When you have to dry very, very wet soils, okay, and need to facilitate the compaction of that, this is when we use some stabilization as well, okay? In this case, the stabilization is usually not considered as a structural layer, okay? So even if the soil was very nice, stabilized, and you have a chemical stabilizing here, a platform, and you ended up with that platform under your pavement, it's usually not considered, okay, as a pavement layer, even if you gain some strength in there. The second will be the strengthen a weak soil and restrict the volume change of highly plastic materials, right? In this case, the modified material is usually given some structural value into the design procedures. And the third one would be to reduce the moisture susceptibility, right? So that's what we do with expansive soils and frost susceptible soils. Ways to stabilize the soil, okay? Those are some of them are mechanical. You do something mechanically to do the stabilization. You put more gravel. Mostly, this is the solution number one, right? The best solution is just get gravel and just use them, right? Get granular material to be larger or thicker, or you blend it. You blend the material that you have, which is pretty weak, with material that is a little bit more, has more competency. Geosynthetics, this is a mechanical way to stabilize it. And the lightweight fields or surcharge, which you probably know in length for compressibility soils, right? We're not going to go to that in here. That's another whole course that I'm going to be teaching. Actually, we started teaching that yesterday, and I canceled my class in Arizona. But it's all about, compressibility and stabilizing the soils. But I think you are familiar with that on your compressibility class. And mixtures, you put a stuff on the soil. So you can put Portland cement, you can put lime, a combination of lime, fly ash. There are many things coming out right now that you can just mix the soil with and just try to create some chemical reactions to stabilize the soil. Asphalt or bituminous material also is used, pozzolanics and slags that are available commercially, and chemicals also to be added. And waterproofers like asphalt and geomembranes are also part of this stabilization method that we're going to see. Let's talk a little bit about the mechanical stabilization methods for pavement, and I brought at the end, you have always the reference that I use for this. There is a very nice reference that is available. It's by Ray Rollins and Rollins, 1996, and they do a very good job on summarizing on a big report the methods for low volume roads. And this one includes, again, like I said, more gravel, blending, geosynthetics, lightweight. They do have tables in here and what kind of soil type you can use this, right? Which one is more suitable, how these improve the soil, and some other considerations that you need to think when you need to decide, right? So you got the problem in there, you need to figure out what soil it is, okay? And if you go over there and check those tables, figure out what are the suitable, methods that you're going to have available for that, and what it's going to do to your soil. For example, blending. Blending is good for soil that are moderately clay material or plasticity, right? So when you do blending, what does that do to the soil? So improve degradation, reduce plasticity, reduce the breakage, and so forth, okay? If you want to add more gravel, that's not very good for clays, right? You can mix it very well. You just can't mix it, right? So the seals and clays, there are no benefits to that, right? You can just use it for other type of soils. And so let's go for some of those guys. So more gravel, right? So stabilization number one is you're gonna have thicker granular layers. Okay, this is, again, I will provide a working platform, which is pretty good. Do not provide the strengthening of the soil, of the subgrade, and it's going to be most often produce disturbance of the subgrade than that benefit. But now you can work on this guy. Used to reduce frost problems, and I'm going to check. Okay, this example. Like, for example, a common practice in the Northwest states in the United States, and actually they use 1 meter of gravel to reduce the heat, for example. So I said, we don't want to get the frost, so they figure out what is the frost depth, okay? And they just put this in material that is not prone to swelling or just, having problems. So that's what they do. They can do, like, for example, Washington State, that's very common to put 18 inches, okay, 18 inches of cap rock, that is called cap rock, beneath the pavement section to mitigate the frost action problems that they have. So this is the way they do it. They do the subgrade, they do the capping here, okay? They do subbase, the granular base, and the pavements. Then you can put any other stuff in there that you need to put, all right? But this is basically the capping layer goes below the subbase material, okay? Geotextiles and geogrids, we're gonna talk a little bit more in length in the second hour. It's used in combination with quality aggregate. We call it aggregate to adopt. And what it does is allows the access to the construction equipment. You put a geotextile, you put a geogrid, and now you can at least have a platform that will distribute the strength, a little bit better. So you don't have punching failures when you just get your road equipment in there, and you got more general failure, okay? You can have failure, but it's general. Reduce the extent of stress on the subgrade. And one of the most important things that is being used lately is in the separation, provide separation. When you do have aggregates penetrating the subgrade, right? You don't know what the thickness is going to be anymore. You're going to have all this blended material in there. And the other one is the subgrade material has a lot of fines, okay? And if you get these subgrade fines invading your granular-based material, you're going to be creating a problem with the drainage, right? And these fines have a lot of suction. They will accumulate water in there, and you're going to have water right below the asphalt pavements of, or any sealing surface that you're going to have if you have an unpaved road, all right? So separation actually is a very important function of the geotextiles and the use. The primary long-term benefit is preventing, again, aggregate subgrade mixing and maintaining, therefore, the thickness of the base and subbase cleaner. Within the admixtures for the soil stabilization, again, Rollins has a very nice table in there in which they use the benefit, or they explain the benefits of Portland cement, lime fly ash, and so forth. So let's go a little bit on some of these guys. What the mixtures do is they do fill or partially fill the voids between the soil particles. Okay, this is what it is. And obviously, we're not talking a little bit about the chemical reactions that occur for some of them in here. But basically, what it does is reduce the soil permeability. So obviously, increase the tortuosity of the flow through this particular material, which is good for us because what we don't want is water on the subgrade material, right? So if you stabilize some of these, then you're going to have less permeability and therefore less water on the subgrade material that is your problem. So create a waterproof surface to protect the underlying layers on that, right? So this is important for that. There also, a problem that is that increase the density, okay? Increase the density of the material, right? And now for shearing behavior, instead of now getting into the contractive because you have a looser material, now you get into a more dilative, right? More dilative behavior for that. So there's going to be some change in the volume change behavior of the soil. And add cohesive strength. Now we can talk about cohesion, right? The cohesion strength. In reality, it does bond the particles together, right? Bonds the particles together. And it could be on a chemical reaction, physical reaction like flocculation, or chemical reaction like cation exchange capacity. Okay. Disadvantages of the admixtures. Well, you need to test it. You need to figure out if that particular material that you want to mix the soil with is going to be okay. There's usually problem with dust control, and there are also problems with the weather dependency, meaning that after a few years, the benefit of this treated material is gone. It's gone because the cycles of wet and dry, stuff like that. And there is an also very big problem, at least on expansive soils. I'm going to go a little bit more in detail on this one. Is this when we have sulfate-bearing soils? Okay, so just always think that when you're going to need to stabilize or just add some lime into your soil, or any product that has calcite in there, you need to first of all check for sulfates on this soil. Okay, this is very important. I'm going to show you why. Hydrated lime, this is one very well used, at least in the United States, for clay materials, right? For this expansive soils, the norm is not to use cement. We use lime, okay? Lime for that, for CH and CLs, and for any clay, gravel, or clay sand that you're going to find in there that you need to do. Why? It will reduce the plasticity. It's going to make the soil less sensitive to moisture changes. It's usually considered when the soil has a PI of greater than 12, they don't even measure swelling. They just, they just go and stabilize. Not a good practice, but that's what they do, right? If they have the money, fine, just go ahead and do it. But usually, may result also in frost-susceptible mixes because the soil is going to behave a little bit more like a silty material, okay? So you probably are fixing one problem, but you might be, making another problem around. The Portland cement is more commonly used in non-plastic soils, all right? So you got gravels, you got, no gravels, but, soil that I need to stabilize more on the granular side or on the less clay material, then we use cement for that. This one is also a guide that is found on the Australian procedure for design guides, for design of pavements. And this one is pretty much a summary of the type of the soils that you can use for a different admixtures that you have in there. For example, cement and cementitious blends, it's usually suitable for soils that are has a more than 25% passing, but the PI is less than 10, for example. Okay, but mostly it's used for those that have less than 25% number 200 passing, but so you can use it in most of them. Usually it's not suitable for soil that are plastic, right? Greater than 20 or so. So this kind of charts is going to help you, okay, at least to do a preliminary guess of what is going to be the best thing for you today to do, depending on the soil type that you're going to find. Here is same, the lime. The lime is used for the clay materials. Bitumen is usually for, more granular material or less, passing 200, and so forth. So what is the chemistry of the lime stabilization of the soil? At least for you to understand what is a problem with the sulfates in here. When you put lime, whether in any form, to the soil, there are three main chemical reactions that are going to be occurring there, right? The one is an immediate reaction, which is the cation exchange capacity, right? Cation exchange and the flocculation of capacity. Cation exchange and the flocculation. What happens is you're adding calcium ions, okay, that will make from the lime, that will replace cations that are like the sodium, monovalent. So the divalent is going to be replacing those which are weaker on the soil, right? So you're going to be making more absorption into the clay surface. This will reduce the diffuse double layer that you have in there, because it's going to be leading to flocculation and agglomeration of the clay particles, all right? The result is going to be improving workability, reduced plasticity, and faster compaction for that. Another short-term reaction that occurs when you put the lime on these soils is a pH increase, okay, a pH increase and dissolution of the silica alumina that you have in the soil, okay. When you put lime in the soil, the pH rises for about 12, 13, and at this high alkalinity, the silica and the aluminum from the clay materials will dissolve in the pore water, all right? So this is something that you're going to have in there. Another long-term reaction that you're going to have is a pozzolanic reaction, right? And it's basically this dissolved silica and aluminum that is now on your water, pore water, will react with the calcium, okay, that you just add from the lime and form cementitious components, right? This is the cement stuff that you always do, right? So calcium silicate hydrates and calcium aluminate hydrates, this is what you form. And these compounds are similar to pretty much a Portland cement kind of stuff, right? And provides long-term strength and durability to the material, all right? So these are pretty much, in a nutshell, what the chemical, situation is happening when you do put lime in the soils that are expansive. In summary, well, the lime stabilization first is going to be improving the soil plasticity and workability through the cation exchange and the agglomeration or flocculation, and later will increase the strength because of that pozzolanic reactions from, to form cementitious soils. All right. How much do you put? It depends on the city procedure or the state procedure or the whether you are here or there, whether you are in the North India or South India, right? So basically, it all consists of what is the best practice or the most, what the experience of the groups in engineering have had. But if you check most of the procedures that are done for that, whether local or, state agencies or national, is about the application of about 1 to 3% of hydrated lime toward the drying of the soil and get the compaction going. and again, there is no gain of structural capacity of the pavement with that kind of percentage that you're adding to this, right? When you use in the stability of expansive soils, when you do a test, sometimes you get more than 3 to 5% of free swell on that odometer test that I show you, the 45, 46 ASTM, and then you just go for that. And again, the treatment depth is limited by the construction equipment. Usually there are 2 to 3 feet that you can treat. Okay, it's difficult to do more than that because of the equipment, right? Because of the mixing that you're gonna need for that. Okay, so now you see that you can, replace the soil, just get rid of it as much as you can, and then you can do 2 or 3 feet of, mixing with this lime and trying to improve it. Okay. Problems with lime stabilization. Certain soils have been seen to produce soils that are prone to kind of a reflective fatigue cracking. All right, and there's been some documentation about that, and may produce also soils that are highly susceptible to frost heave. All right, and it's basically, like I said before, the soil is going to start behaving more like a silty material, right? It's gonna have, if you allow some water going on in there. And this is basically happening if the curing period that you got is not enough. Okay, if you had a very nice stabilization, probably you're gonna be okay. But if you don't let this cure enough, then you may have problems with that. Lime should be between 3 to 8% of the dried weight of the soil. That's another formula that I found. And mix should have an unconfined compressive strength of greater than about 50 psi within 28 days of curing. Lime stabilization methods, they call for a minimum compaction of 95% density. As per the ASHTO T99, which is the ASHTO to do your granular based material and cement treated soils. Okay, this one again is in Rollins and Rollins. There is a nice table in which you're going to see for every type of several soil that they have been dealing with, what is, as you put more lime content in there, how much you're going to be improving your liquid limit, your plastic limit, and your PI. Okay, so that's why we know there are some soils. So obviously, if you can do some testing in the lab before going into the field and trying to figure out what is your optimum lime, so to stabilize the soil to a point, right? So you don't go too much on that, spending more money on that. And also for the QU, the bearing capacity on that, or the unconfined compressive strength. So there's some information in there for you to see. And you can see here, for example, that you have soils in here that when you put, let's say this one is high plasticity clay from Illinois, it's called Brico silty clay, and you have a PI of 29. When you put 5% of lime, you ended up with a non-plastic soil. Okay, so this is the kind of improvement you're gonna get. So there are some dramatic improvements on that for sure. Okay, this is the effect of lime content on the soil properties. This is usually, I give my students a question on that. It's not on your exam today, okay? It's not on your exam, but basically how the strength improves with the adding of lime content, right? Okay, so basically the strength will improve. The length change, which is the shrinkage behavior on the linear shrinkage test, is some simple test that has been done also. You see the dramatic change on that. The swelling also is reduced. The swelling pressure is reduced. The liquid limit is reduced. Plastic limit a little bit high, and therefore the PI goes down. Okay, so there are all these, and you can check your soils and figure out what is the lime content that will just stabilize your soil so you don't go too much. The durability of the lime soil mixture, and I focus on lime because this is the main mechanism that we use for expansive soils, right? That's what I do that. So that may be affected by environmental factors. Water is one of them. Most lime stabilized soils retain the strength and the long-term condition. But when they get exposed to water, there has been reports that there is a poor strength retention for stabilized soils exposed to these soaking conditions, right? Freeze-thaw cycles, it seems like when you do freeze-thaw in several years, you do have some deterioration of this material. What I'm saying is, if you're going to be cement stabilizing something, you may think that this is not going to last forever, okay? It's not going to last forever. If you have any of these conditions that can be improved, so you may consider that. Leaching of the calcium, usually you got the calcium on this one, and that's going to decrease, obviously, the cation exchange capacity that already occurred, and basically there is a reverse in the beneficial of the reduction in the plasticity of the soil. In other words, the soil will gain plasticity again, right? Carbonation caused by the combination of the lime and atmospheric carbon dioxide, and that makes to form calcium carbonate. The calcium silicate and the aluminum hydrate, and also reverts to the original silica and aluminum form when that happens. And sulfate attack. Sulfate attack, I'm gonna just give a dedicated slide to that one. This is a very important one. You have sulfates that are present in the soil water, all right? Some soils do. Some agricultural soils, for example, have a lot of sulfates because they were used for the plants, and now these areas are now into the urban development, and there were a lot of sulfates left behind on the groundwater and the soil water around. When they combine with the calcium that you're putting there from the lime or the aluminum from the clay minerals, they will form ettringite. Okay, this and actually vermiculite is the other one. This one has a volume change that is more than 200% larger than that of its constituents, meaning that you're trying to fix the swelling potential of a soil, right? But if you have sulfates on the soil and that sulfates combined with this calcite, okay, you can form a worse problem in there. Okay, as a matter of fact, in Arizona, about, I would say, 25 years ago, we were just expanding upon the north side of the city, Phoenix, and basically there were a big urban development going on in there, and one of the companies was hired by the local authorities, the county authorities, to make all these roads. Those were all on expansive soils, right? They were just street roads on expansive soils. Basically, they go over there and they spend a lot of time and money, and they build the county, and a year later, all of these roads are absolutely cracked and crazy, all right? So the soil is going up and down, a lot of cracks all over the place, longitudinal cracks. So what happened here, the asphalt mix was okay, the formula was okay, the thickness were okay. When they figured out the soil had a lot of sulfates, and they did not check for sulfates, all right? I mean, that got bankrupt, the company got bankrupt. Obviously, they have to pay back, redo all of this work. And the sulfate test at that time cost about $100. I mean, nothing, right? Nothing. So just a simple thing like that, okay, will bankrupt a company, your company. So you need to be very careful with this. Sulfates are and everybody put lime on these soils, everybody. So you need to make sure that you don't have. Vegas also had a big problem on that one a few years ago, like 6 or 7 years ago. I mean, I'm talking about now. I'm not talking about 20 years. We have experience with that. We know what's happening, and people are still making mistakes like that, okay? We engineers making mistakes like that. This is a massive irreversible swell in our core, okay? So the road or any light structure put in there is going to be damaged. It's difficult to predict the combinations because, you may have sulfate contents and stuff like that, and they may combine. If they're soluble, fine, they're going to be more prone to combine or not. So it's difficult to know how much calcium is going to be forming out of the lime. So you better take provisions about that. So if there is a suspicion of possible sulfate attack, okay, the lime stabilized soil should be tested in the laboratory before that. Okay, so you need to test for that, and basically is going to be introducing water into that to see to make the sulfate soluble and see what's going on, right? So there are some tests available for you to do to make sure that that's not going to be a problem. As for cement stabilization, I'm not going to talk much about it. A low cement contents, the product is generally termed cement modified soil. That reduces also the expansivity, reduces the frost susceptibility. And at higher cement contents, the end product is also termed soil cement or cement treated base, CTBs, right? That's where you see those in the report, subbase or subgrades. These are the proper mixing for a CTB or cement treated base. I'm just putting here, some of the considerations for you to do. The pI should not be high, okay, should be on the low side if you want to use that on expansive soils. Again, the king methodology or a mixture we put is lime, but we got also people putting cement on that, right? So use it if your pI is less than 20. If the passing number 40 is greater than 45, this is what the ASTM standard said. The cement content should be somewhere between 3 and 10% of the dry weight of the soil. Again, all of these should always have previous laboratory tests for you to know how much you can put in there. Unconfined compressive strength should give you 150 psi or more than 1 megapascal within 7 days of curing. The CTB should be compacted to a minimal density of 95% of gamma D max as per the ASTM, the M134 for CTBs. And usually you use type 2 cement that has greater resistance to sulfate attacks, sulfate resistance, or type 3 cement has greater strength. So you need to play with whatever cement that you're going to need to use, right? Durability. Organic matter and sulfates are the enemies for cement treated material, okay? Tests must be conducted prior to use. If you have organic matter and you cannot avoid that, some inhibit the hardening process for that, so just test. There is a test that is done, and I brought this one in here because I had a question in here about organic material that you're gonna need to do some stuff on this. And if the pH of a 10-to-1 mixture by weight, okay, of the soil and cement is greater than 12, that's what I found. After 15 minutes of mixing, then the organic matter should not be a problem. All right, so you can just deal with that if you, but you need to stabilize it, of course. All right, you need to stabilize it. Sulfates, again, I already talked about that, but the resistance to sulfate attack differs for cement treated, coarse grain, and fine grain soils, and is a function of the sulfate concentration on your soil. The use of cement for fine grain soils containing more than about 1% sulfate should be avoided. There are tables about the parts per million of sulfate content that you need to avoid, or when the susceptibility to sulfate attack is higher or lower. I didn't bring them in here, but you may have some of those too. Here is a step, and probably I'm not gonna go. Probably, yeah, why not? Still time. The genetic and mixture design, and this is just for your information in here, and how these professionals do their work. Okay. Usually, and again, this one is based on experience, based on many years of trial and error. This is, ended up being the standard for the city or the state. Okay, so you classify the soil to be stabilized. You usually do grain size distribution, NPIs, prepare trial mixes with varying percent content. If you are using lime, you select the lowest percent with a pH of 12.4 in an hour, and that you can get. And if you're using cement, use table to estimate the cement content requirements, and there are tables available for that. If you're using asphalt, there are equations and tables in this particular rollings and rollings, okay, that I had the reference at the end of the lecture in here, in which you can estimate the quantity of the cutback asphalt that you need to use. So all of them are, there are things that are available. Right. So the next, once you prepare the trial mixes to see how this mixture is going to be working for your soil, you develop moisture density relationships for the initial design of the treated material, right? That's going to go in there. Then you prepare triplicate samples, and this is something that payment people do. We don't do triplicate. I don't know how many samples you do, but usually we don't do many, right? You duplicate samples on, because it takes a lot of time, but the more samples you do, the better, and cure specimens at a target density. Determine the index strength that you're going to have. Usually it's an unconfined compressive stress. You just break the sample and figure out what is the unconfined compressive strength. I show you a couple of target densities before, but there are standards for that depending on the use of the soil that you're going to have. And for the asphalt, which is out of our thing, they do Marshall stability. Payment people in here, I'm not going to get in there. Determine the resilient modulus for optimum percent admixture, okay, and perform test or estimate using correlations, like we saw it before, and I shouldn't put chapter 5 in here, but lecture 5. And conduct a freeze-thaw test if the regional is, you are in a region and is required when you have this mixture. So these are pretty much what you need to do, or the considerations that you have to do on that. Again, there are manuals that we're going to get you into that, but I wanted for you to introduce to something that probably you haven't seen before, okay, if you need to talk about, if you need to work on a payment geotechniques problem like that, okay? So with this, I hope you just get into this without fear of, there are information in there for you to check. Do you have any questions for the cement and mechanical stabilization before we get into the geosynthetics? All right. So much time do you having here? 10:30. What time did we start? We started at 10, right? So I got 20 minutes. Okay, we're doing fine. Geosynthetics. Any questions? Any questions on the online audience? That was clear, huh?
Professor, is carbonation a problem in cement treated bases? Is carbonation a problem in cement?
Yes, and yes, it is. We mentioned that, yeah.
From what I read, usually you have Portland calcium hydroxide in a cement treated base, which deposits because it needs sufficient volume. Calcium hydroxide, so it deposits on the surface of aggregates. So that is why when we do a split tensile stress, the interface is along the cement matrix and the aggregate surface, because that's the weakest plane. So when carbonation is happening, this calcium hydroxide converts to calcium carbonate in the presence of calcium dioxide, right?
That's correct.
So we are improving that plane. So that is a benefit, right?
Yes, yeah. That's correct. Well, the carbonation occurs for sure, right? When you have that, when you have at least this thing. But yeah, there are ways to improve it, right? To improve it, and if you catch it when that will occur, which is going to be in the surface, right? Then you can do something like that. I'm not familiar with that kind of improvement for doing that, but certainly it's something that you need to consider on the design. Okay, and what you said is this is what exactly happening. Yeah.
Prof.
Yes, sir.
Good morning, Prof.
Good morning.
Actually, I would like to ask the question further, when we have to conduct a freeze-thaw test, so for which test we should go for conducting, how to measure for this shortage, the improvement, how we could say the improvement has been done, considering the effect of lime or chemical in this cement treatment.
Yeah, there are methodologies and procedures to do the test prior to try the treatment in the field. How do you recognize if that is not gonna? It's not that it's gonna be improvement. Is what you're trying to recognize is that if freeze and thawing cycles are not gonna be a problem to your stabilization chosen technique, right? That's what you need to find out. So there are, indexes when you said, okay, once you have that, if we have freezing and thawing, you subjected there is methodology, didn't bring them in here, that you're gonna be doing that, submitting to freezing, thawing, okay? And they're gonna have some indexes in there that said, okay, the water when you're thawing, how this, and it's usually, I think it is with the unconfined compressive strength, okay? So basically you do several, samples, and you submitted this one to different cycles of that, and you measure how much reduction in the unconfined compressive strength after a certain number of cycles, okay? So that's exactly what I think they do, but I didn't bring the methodology. Does that answer your question? I think it's the confined compressive strength, yeah. All right?
Hello.
Yeah.
Here.
Hello. I just listen like that.
No. How sensitive is this method with respect to the temperatures, ma'am?
Temperature, well, freeze and thaw is a problem due to temperature, right? Is the temperature per se that brings the soil to freezing and thawing. So admixtures are prone to fail if you submit them to changes in temperature, right? But this is pretty much that. Now, if you're talking about stabilization when you don't have freezing and thawing, but you do have expansive soils that go into cycles, or a place that goes to cycle of high temperatures and low temperatures, I haven't seen any problem with that. Unless, the problem is the moisture ingress, not the temperature for that kind of stuff. But obviously, if you got into the lower temperatures, that's going to be an issue.
Excuse me, ma'am.
Yes.
So I have two questions.
Yeah.
One, like in India, we have a practice, say, when we are using CTB. So the resilient modulus of CTB, we calculate using the unconfined compressive strength empirical formula is there.
Mm-hmm.
Now for same, say any soil is there, and we have used some admixture, chemical admixture, and the soil got hardened. Now it's UCS.
And the soil what?
Soil is hardened a bit. So it's, you can see UCS is improved. Unconfined compressive strength is improved.
For expansive soils.
Yeah.
Okay.
For that matter, we will take expansive soil.
Mm-hmm.
So basically that unconfined compressive strength of the subgrade has been improved using the admixture. But in our say KNPAVE or any software we are using, say linear elastic theory which uses, so it takes a resilient modulus for the sake of calculation. But UCS will give you compressive strength, right?
Right.
And we use that empirical formula for the resilient modulus.
Do you think it's correct?
Yeah. Okay. So that resilient modulus is not correct.
Exactly.
So how to incorporate that?
Well, I'll have to check, but I'm very sure there are correlation between an unconfined compressive strength. DCP, dynamic control. This is dynamic, but there are some measurements of strength like CBR, right? So I'm very sure there are ratios that you can get between the unconfined compressive strength and resilient modulus. That's the best we can do on that one. If you don't do resilient modulus, the model or the program that you're working on asks for resilient modulus. Usually you're going to have to use a way of correlate the unconfined compressive strength you get with the resilient modulus. You just can't use it, you just can't just go and put that number in there. You need to figure out a correlation between that, okay? Like we did for the CBR. I just don't find, and I'm trying to figure out if I know of any of them. I'm very sure they're available because this is a very common practice for that. But for the latest models, we're using resilient modulus, right? More than a strength parameter that we used to do before. And you know the reason now, right? Because the strength parameter is only a function of your octahedral stress, and then you don't have that, it's not a good thing. It's just the strength, right? The deviator stress. Excuse me, deviator stress. Shear strength of the material. So it's not a good measurement. It's not sufficient, I would say. Okay, it's not sufficient. So I'm going to try to find out a correlation. Let's try to find out a correlation, because you should not just put the values right there. All right, great questions. So let's go. I'll talk a little bit about geosynthetics again, and those are just very general considerations, but I think it's important for you to start into this world if you need to go this route of improvement of the soil with this mechanical base stabilization program. So you should be able to describe at least 2 geosynthetics that can be used in pavement applications. You should be able to list at least 5 pavement applications involving geosynthetics. Itemize the geosynthetics functions that are involved in 3 pavement applications, and explain 2 pavement applications involving geosynthetics. So that's some of the objectives on that. I mean, this is where I'm going right now with these general considerations. Okay. So I usually bring to the class a big bag of geosynthetic samples for you to check. I didn't bring them here, right? So I hope you've been able to touch them and to see them, and just, if not, I recommend you that. I'm very sure there are going to be places where we can, ask for samples. I don't know if Professor Barat has some samples here. Great. So you got the samples in here. You've been looking at that before, in improvement. But basically, we do have, I kind of, we just put it in different categories. Geotextiles is one of them. You can have them being woven or non-woven. I'm very sure now, understand that you are familiar with that. And geogrids as well, okay? So we do have also the geotextiles is a textile, it's a fabric, right? And you can see pretty much when they're woven and when they're not, okay? They're just put together like that and placed out. Mostly polypropylene, that's you're gonna have in there. You also have geocells, and geocells are very interesting. If you're going to this congress or have this, you just basically open it and fill it up with soil, and then you just basically make a big layer, right, or a stabilized material being that way. Geocomposite drainage products like wicking drains. Basically, you do have geotextiles and something, but then you have kind of I'm going to show you in a minute, some wicking elements or fibers in the middle that you can just get higher permeability for the wire to get out of it. Okay, so that kind of a composite material. And erosion control products also, you can just put a stuff on top of your slope and being able to just protect from erosion while you still can let the vegetation to grow. Okay, so there are many of them, and everyone has their own specifications and used for different applications. So what are the functions? What are the functions of geosynthetics in pavement systems? This is Corner 1998, and basically we use them for these particular functions, okay, in pavements, right? The first one is going to be the separation. We talked a little bit about that a little bit earlier, and this is basically when you put this one between the subgrade and the aggregate base in paved and unpaved roads, right? And airfields also you can do that. Or between the subgrade and any ballast that you're going to have for railroad systems, right? This is also used on this kind of application. Or between old and new asphalt layers. So you just put them in the middle, and you're going to see that one in a minute right here, right? So separation, reinforcement also of weak material will be our second function for the geosynthetics. Those are different, and that's what you need to think about first. Okay, what is that I want my geosynthetic or my geogrid right there? What do I need? Okay, so and this one, then you start getting to that. I think if you understand or if you know your problem well, the first thing you need to know is if you need separation, reinforcement, filtration or drainage. Okay, that's the first thing you need to get when you're using geosynthetics. It's not okay. I want to reinforcement for what? What do you want to do? Okay, what is your final goal? Okay, so reinforcement of the weak materials. Usually you put it over the soft soils for unpaved roads, paved roads, airfields, railroads, construction platforms, etc. Reinforcement, usually you can reinforce between asphalt layers. You can between the asphalt layer and the granular base. You can do that one between the base and the subbase, and you can do it between the subbase and subgrade. Okay, wherever you need the reinforcement, you can put that one. Filtration beneath aggregates base. Base for paved and unpaved roads, and also for airfields and railroads. And this one use the filtration right there. And separation, like we saw that one, right? This one is right there. And the drainage is an interceptor for horizontal flow usually, and drain beneath other geosynthetic systems if you need to do that. Right? So, and that also can be put right below the surface when you don't want the water close to your asphalt pavement, okay? Or you can put it on top of the subgrade so to get the water out when it needed before it gets into that subgrade. So what are the applications of geosynthetics on pavement structures? Again, the first one is probably the mitigation of reflecting cracking, and this is when you start putting that one between asphalt layers, okay? One of them. And basically, you just get all these cracks in there, and you just want to resurface, right, to eliminate those cracks. Well, even if you resurface with nothing, probably what you're going to happen is you're going to get the reflective cracking showing up again in a couple of years, right? So basically, you want to avoid that, or just to get the length of the maintenance a little bit longer, and then you just use it for mitigating reflective cracking. Separation of different materials. Stabilization of the road subgrade and granular bases, and improvements of drainage. Okay, so these one are the applications for the geosynthetics on pavement structures. Mitigation of reflective cracking. I've got a couple of slides in here for you. And again, we can mitigate cracks that are alligator cracking, or are longitudinal cracking, or fatigue cracking. Again, the reinforcement for that is going to be put with thin layers or between the asphalt layer and the granular base material, right? Just get like a barrier for that propagation of the glass. If you got a cement treated base, also they might get cracks, right? They might get cracks and they will reflect on your asphalt. You don't want this to happen, and that's why we just start getting into, putting those to avoid that, okay? The problem of reflecting cracking in the asphalt overlays, it happens, again, it can happen because of shearing behavior. Okay, you got all these cracks going on in here, or just the bending. Those wheels are going on and they're just bending some and just getting into the cracking, or just basically thermal cracking as well. Okay, you got temperature changes and you start getting into the thermal contraction and dilation that will create a problem. This one is, for example, a typical reflective cracking in asphalt overlay. The thermal cracking, you're going to recognize them because they don't go longitudinal to your pavement. They're going to go transverse. Okay? When you get the transverse cracking, you say, okay, this is a thermal problem in here. Okay? When you get the longitudinal cracking, you just start checking into the expansive soils or some other, a failure mode for longitudinal cracking. So again, you just go ahead and, you got all this crack pavement that you need to, rehabilitate. Before you put this one, then you just create the asphalt reinforcements right in the middle, right? So you avoid that all these cracks will just propagate upwards. Okay. Mechanisms that are necessary that you identify in order to use those geosynthetics on pavements. Okay. Again, you need to figure out if you want a moisture barrier, if you want a stress relief, okay, or if you need reinforcement. All right. The geosynthetics moisture barriers involves mechanisms like minimizing the water infiltration and maintaining the low moisture in underlying layers when you don't want this change in suction to happen too wide, right? Because then you're going to get that problem on volume change. The stress relief involves mechanisms of releasing the energy of the crack propagation. This is a typical case for that. And the third one is the reinforcement mechanisms, which is the distribution of all those strains that you're going to get from your traffic into a wider range. Okay, so development tensile strength that keep the confining of the underlying damage layers is important on this one, and we're going to see that in a minute. Okay. I just brought, because it's good, usually we as geotechnical engineers, we don't get into the construction side of the job, which I think this is the fun part, you know. So I brought a couple of slides in here how they do that in the field, but certainly there are many literature that you can see the steps that they use in construction to do that. So first of all, they need to prepare the surface for the pavement fabric that you're going to be pulling. Usually is miling the asphalt. Okay, miling is basically you scarify and you take few centimeters of this one, so you create a rough structure in there. You dry it and you clean it, you know, vacuum free of material. If you have cracks that are larger than ½ inch, you should be filling them with some material. You just don't want to just put the stuff on top of it. Then you just apply the asphalt sealant. There is a tack coat that you get. It's just kind of an oil that you go ahead and do it. And this is nice. We got every year by November, we do have asphalt material. It's called asphalt material, pavement material conference in Arizona. And I'm always, you know, fighting to put a geotechnical section into this one, right? Because it's everything about pavement that nobody talks much about, you know, geotechnical. So we put this one. But the nice thing is, with geotechnical, we are able to go and see this kind of, you know, demonstrations in that. So if you have some demonstrations around, if you see anybody paving or putting geosynthetics, you know, that's something that. Another thing that I do is I keep my hard hat in my car. So when you see something going on in there, you just, you know, put the hard hat and ask permission to get into the place, and they usually do it. Okay, they usually let you go over there and see what's going on in there. So that, you know, being curious about that, you learn a lot of stuff. Okay, asphalt cement, you put, you know, the tack coat, and then you just install the pavement geosynthetics on top of the tack coat. Okay. And basically they can do it with a mechanical means. You know, they have machines where you just roll the stuff. You know, it's pretty sophisticated to me, I think. Or you just do it by hand, right? A couple of guys, you know, and just, you know, you need to be very careful not to have wrinkles and things like that. So it's a little bit of art on this installation to do. And the last thing is they place the asphalt concrete overlay on top of that, right? So you just, you know, put the asphalt overlay in here, and usually you need to put at least a minimum of 1.5 inches, okay? Because then your traffic is going to damage your geosynthetic if you don't do that. Anyway, I wanted to just bring this one in here, and then, you know, there's some testing for the cracking, and it shows that, you know, if you do have the cracking before, then you just have the cracking, you know, disappearing, at least for a while, when you do have this geogrid placed into the asphalt layers, okay? So that thing works very well. And I bring this in here because usually geosynthetics have been an area when it hasn't come from the academic side to the practical engineering, has come from the practical engineering. They start making a lot of money, and now the academics are looking at that and said, okay, what's going on in here? What kind of mechanisms we have, right? How can we improve that? So they're way ahead of us on this. Separation application, it's an easy thing, just I'm not going to go much on this one. You put it between base and subbase or subbase and subgrade, and basically it eliminates the problem when you do have, gravel getting into your, soft subgrade, or the subgrade getting into the, just into the fines and just basically, damaging your asphalt drainage system, your layers that have drainage, right, on this one. So this is important. We have made, and I'm very sure you have, over there, the granular-based material cannot have more than 10-12% of fines, and some of them have more strict than that, okay? They should not have more than 8% or, to 10% of fines, right? So the problem is when that granular material is sold to the state to do the roads, they sell it, and they sell it without washing it, right? It looks good. Well, then if you wash this one, you can see that those material has about 16%, okay? 16%, because when they check it, they don't wash it, right? So we did a lot of testing on resilient modulus and the moisture accumulation and the suction accumulation of those fines, and it's a tremendous problem that you do have if you got 3-4% more fines into those granular-based materials. So you want to avoid fines in your granular-based materials, all right? Arizona has no rain, all right? I'm talking about 6-7 inches a year, okay? Just multiplied by millimeters here, right? It's very little amount of water, okay? But you go over there and you core through a pavement, and you see water in that granular-based material. Granular-based material that is not, 40-50% degree of saturation or less, the granular material that has 85-90% degree of saturation. So the problem is the moisture that is going for, because we do have huge temperature changes, right? We can have a sweater during the evening, but we have 40 degrees during the day, right? It's a desert. And basically those changes creates a thermal gradient that brings all this moisture, right, from whatever place it is that it has to be, and that is being retained by the fines that this, granular material. If you have no fines in there, the water is gonna, it's not gonna survive right there, right? It's gonna get away. So those are cases that you need to take into account, that this is what, it could damage your road. That. Separation, already went through that, or without geotextile, and with geotextile, we just, the aggregate intrusion and the soil pumping will be eliminated. And the longevity improvement, there are no procedures, there are no design guides that include the benefit of the geosynthetic per se, at least not official in the United States, okay? Do you guys have any of that for those working on the field? There are no, okay? So there are ways that people have tried to measure the benefit of that, and I'm going to go that into the second hour a little bit, in more detail. But this one is pretty much, what we have done for that. And this one is how to figure out how to improve it. This is Alcari. And basically what it does is just, trying to figure out that without geosynthetic and with geosynthetic, which one is the amount of easels that you can sustain on the road, okay? Equivalent easels means the amount of 18,000 pounds wheelers, right? Equivalent to those that you can just get into your road, right? And this is the W into the AASHTO payment equation. And basically you can see the benefit as you go, as you have more load, you're gonna have more benefit. All right. So course like this you can find, and paper like that you can find. Do you guys have any questions with that preliminary thing on the geosynthetics? I hope you guys learn, and I get you interested in some of that stuff, in some of these things. All right, 11:06. So I'm into your, break, tea break. Yes,
Sorry, Prof.
that's okay.
Actually, I have one question. Is in terms of comparison, which ones perform better in terms of stabilization technique for the subgrade soil, which is subjected to either zero temperature or freeze-thaw cycle? Means if we are comparing geosynthetic or the chemical techniques as a stabilization technique. Considering to means this is for both roadways and railways, as both goes through the moving load or the cyclic load repetition cycles. So which one performs the better? Can you please explain?
I've seen many applications going towards the geosynthetics. Again, the mechanical main way to deal with frost, conditions is being to get this amount of gravel high. Okay, and that's a mechanical way of doing this. So if that doesn't work, I've seen, or at least I've seen people trying to do the analysis, the economical cycle analysis, to see what happens if you do that, or what happens if you start putting geosynthetics and reducing the stuff. So there are many studies going on that, and it seems like a geosynthetics is not a bad idea. It's not a bad idea, because getting granular material of a certain quality in many areas is not easy. Okay, there are some areas that have a great quantities of material, but some areas that have to bring it from far away, and that creates an extra cost to your construction cost. So at the end of the day, it's going to be what's going to be costing less, right? And if the two of them work, what's going to be costing less? If you have gravel availability, probably that's the way to go, mechanical stabilization. But if not, and if you're going to be, more cost associated to that, then probably stabilization with geosynthetics is going to be the right way to go. All right, that answers your question? Okay, you're welcome. Any other questions? I guess I'm very sure we're going to have a lot of more questions on the break. So let's go ahead and come back in 20 minutes, 25 minutes. All right. What happened with the ballast, right? That the material that you use is a little bit different from the one that we have, right? Apart, if we're talking about subgrade stabilization soil, then the lime treated soil is the way to go, and things like that. If you are in an area when you have frost heave, probably gravel, increase of gravel depth will be the way to go. But if you're talking about how the stabilization of the ballast by itself is going to be, right? The problem with the ballast, what I understand, I'm not expert on that. There is a big group in Australia working on that. It's great. And basically, what happens is the ballast trying to spread out, right? Trying to spread out, and basically just lose the strength because of that lateral spread out. Okay. In that case, geogrids. Now, geogrids below this one will allow for the interlocking of the particles. Okay. And we create basically a way to just avoid that straight up. Okay, we're going to see that a little bit of the mechanism here, but that is what I understand. It's been working good on that. Anybody has any better idea? Yeah, the geogrids. Mm-hmm. 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 Yeah. So that will be yeah, to me a very good. Geosynthetics are working fine. I mean, just we need to realize more the mechanism and how to include into the design procedure, right? How to quantify the benefits of doing that, so we can compare with traditional procedures. I think this is our job, right? Our job in the universities more than anything else. Tensar, Solmax, all of these companies that are very good at geosynthetics, they're geosynthetic companies. They have their own design procedures, right? And they're free. You go to Tensar and you download Tensar. I don't remember the name, but it's you get it for free. And it's incredible. It's actually very nice. They said, okay, I do have this frost action, and you're going to see the granular base increasing in here. They have a very nice animation of that, right? Well, you go behind these things, some of them are mechanistic, found, but some of them are very empirical, that, and they not only do that, they change your asphalt, how much asphalt, granular base, all of this, when you put the geosynthetic or without geosynthetic, and you give them the comparison of the prices below. What costs you to put more gravel in here or asphalt in here? What costs you to put this kind of one geogrid or two geogrid layers or something like that. So it's amazing the job that they have done on that. And there are some of them that are very rigorous on that, some of them that is just empirically, right? Empirical. So these are the stuff that we need to check, in order to improve, right? Improve, or just trying to figure out if what they're doing is mechanistically correct. Yeah. Sure.
I'm just adding to the second last question that the person asked about the railway embankment. As you correctly said, for the last we can put a geogrid, but what if it is subjected to railway embankment resting on the soil?
Subjected to what? I'm sorry.
The drainage condition subjected to what exactly? So what if means there is something some deterioration having happened in the railway embankment? So how to mitigate that particular? Is it the vertical drains going to be effective in that case?
Well, the nice thing about ballast and drainage is that you do have a very low suction values for ballast, right? You got granular material in there. They don't retain water. So it's good because they drain easily, right? Now, if you have water in there and you don't want the water to go into the subgrade, and you're talking about, okay, we can use geogrids, but if you want to improve also the drainage, there are composites, and there are some that are geogrids, okay, together with kind of a drainage fabric or wicking drain and stuff like that. And there are composites between geotextiles and this wicking drain as well. Okay. Nice thing about this, I think the air entry value of those guys on the wicking drains are about 75 kilopascals, which is much higher than the one for the ballast. And what happened is that this guy is gonna get the water in. Okay. If you put a wicking drain in a clay, the clay is going to retain the water. So if you had, when you have almost saturated conditions, the wicking drain will work. But if you do have unsaturated conditions, dry system, the suction in the soil is going to be much higher, all right? And basically, it's not going to release the water to your wicking drain. It's not going to release the water unless you squeeze the water out with some other stress component, right? Like, putting something on top or just releasing that. So yes, there are some composite geosystem that you can do. Vertical drains are always work, if you need to, get the water directed to a certain plane, you always, can do some, sand columns or stuff like that when you can get the water in. I think at the end of the day, it's not that we don't have solutions, is the solution that is most economical for you, right? So I think that's at the end of the day what is not the best solution. The best solution is whatever you can do with less money, right? And it's still right. So yeah, this is my take about the composite geotextiles. I think they might do a good work for this kind of materials. All right, guys. You're welcome. Okay, so let's go and have some tea, and we just keep talking on the tea place.
Ma'am, one more question.
Okay.
From mine, like, what will the effect of aperture sizes of geogrids in the subgrid for? Suppose the basic function of geogrid will be the improvement of the strength, right?
No, the basic. You saw there are many of those, right? You know, there are different functions, right? The strength is one of them.
Yeah, like how it is going to contribute towards the drainage. Geogrids as a part, like
the geogrid has no component on the geotextiles. Yeah. Okay,
yeah,
geogrids are a big, you know, kind of a net.
yeah,
Okay.
like if
So
the
and they're
aperture
very
size,
thin, so they're not gonna make a, you know, they're not gonna make a place for you to get drainage at all. Okay. So you're gonna need some geotextiles or something that really direct the water out. Okay, that has some fabric that will just get those channels out, and they are available for drainage. But geogrid itself is more about the interlocking of the particles if you have granular material, okay, and the distribution of the stress if you have lateral spread out of your materials on the granular base. So this one is like the way we've been using it. It's not about the strength. You don't get a strain. Okay, you're gonna see that in a minute. Okay, the bearing capacity. You just change the bearing capacity from a punching local shear failure to a more general failure. That's what it does, pretty much. Okay, good question. All right, that's okay. All right, let's go have some tea now. I'm trying to have tea here for the last 10 minutes. No, I'm just kidding. Okay, questions.